Okay, hopefully this is a good volume. Everyone can hear me? Okay, thank you very much. So I would like to review the event that we all saw in our news feeds a little less than 2 months ago, the crash of the European Space Agency's ExoMars Schiaparelli lander. This was October 19th. And to review what happened, we had that the parachute deployed at an altitude of 7.5 miles when the lander was going at a speed of a little over 1,000 miles an hour. The heat shield correctly ejected at an altitude of almost 5 miles above the planet's surface. And then something a little bit concerning happened. Specifically, the IMU miscalculated the saturation maximum period by just a little bit, we think, by 1 second, right? And this by itself was not a deal breaker, but it led to something more concerning, which was that using that data, the navigation system calculated a negative altitude. Now, using this wrong data, several other bad things happened. Specifically, we had the premature release of the parachute and the back shell. We had the firing of the braking thrusters and activation of on-ground systems when the lander was not in fact on the ground, but was 2 miles above the surface. And of course, all of these bad things led to the ultimate bad thing of the crash at 185 miles per hour, which is not something that you can mitigate and recover from, right? And as David pointed out in the last talk, thank you so much for that great segue, this is, of course, not an isolated incident. Sadly, there are a lot of prominent missions that have been thwarted by similarly, seemingly small things. And one of the most important things we can do at this point is ask ourselves, how could we fix this? How can we look into the future of the next lander, the next spacecraft, the next autonomous system we're going to launch, and try to do it better, try to not run into the same problems that we've run into in so many past missions. Specifically, we can say that there are some runtime sanity checks that look like they would have helped in this situation. One of them is just having a sanity check saying that while you are descending toward the planet, your altitude cannot be negative, right? Altitude should be in a certain range. We expect this to be a positive real number, not a negative number, not a string, right? So checking something like that would have been a real help. We can also say that, for example, you cannot fall faster than gravity. What's more probabilistically likely, that someone changed the gravitational pull of Mars or that your data is bad, right? So we should ask ourselves these things and then be able to know, maybe we should look at that again. Relatedly, we can say also that the delta, or change in altitude, must be within some kind of nominal parameter. So you can't go from 2 miles above the planet's surface to underground in one time step. Again, it's highly probabilistically unlikely that someone suddenly invented a Star Trek-style transporter and transported your spacecraft underground. It's significantly more likely that instead you just have bad data, right? And of course, it would have also been really helpful if we had been runtime monitoring for something like that the saturation maximum has an a priori known temporal bound. And maybe if we had looked at that, we could have even stop some of these other uses of bad data even earlier. So when we look at these things, we say that these are the kind of capabilities, these are the kinds of observations we need to make in order to enable autonomy. We're talking a lot about autonomy here, and autonomy basically means replacing the humans, right? So when we talk about enabling autonomy, we need to ask ourselves, what is it exactly that the humans do? And then how are we going to replace that in a way that makes sense, right? And one of the very first things that we have noticed that humans do very well, right, is that they pilot the system, either on board or remotely. And of course, we've gotten quite good at autopilots. We even have autopilots that fly things that humans can't fly at this point. So then we move on to the question of humans provide self-awareness. How do we do that? You know, if a human had been on board a, for example, landing spacecraft or aircraft that was saying that it thought its altitude was negative and the human was looking out the window going, no, 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 the ground is definitely down there, right? this human would have been able to provide a kind of self-awareness that we seem to be lacking in a lot of our current missions. And how we provide that is through system health management. So we really need to look at how we can get better at system health management to enable this essential capability for autonomy. Of course, humans also are there to respond to off-nominal conditions, and we've heard several very excellent talks at this workshop on things like automated replanning and learning. And we would argue that having better self-awareness and system health management data that can feed into these planning and learning algorithms could only serve to make them better. And of course, the fourth major capability we have from humans is that they make the tough judgment calls. And in some cases, we're quite good at replacing that too. For example, there are documented scenarios where TCAS in the cockpit of a commercial aircraft has made some tough judgment calls even better than a human that was present. But in the end, this one is still a very tough problem, especially when we consider things like ethical questions. Still, though, it would benefit from increased awareness of the system so that we had more details on which to make these tough judgment calls. So here we want to focus on system health management because it is such a requirement for the autonomy that we want to see in the future. And one of the ways that people have successfully done some system health management in current research is through runtime monitoring. And just to be clear on what I mean by runtime monitoring, I have this diagram for you on the slide, where first you will initialize the system, or most often a subsystem, a component, right? Then you will wait for the system to update. You will then ask upon a system update, did the state of the system change? Am I still in a good place? If the system did not change, then you can go ahead and wait for another update. If it did change, then you want to ask yourself, okay, well, now is a requirement violated? Am I somehow in an unsafe state, right? If not, then you say, okay, that system change was fine, and we'll go back and wait for the next one. If so, then it's important to send an alert of the property violation and reset the monitor so that you can continue catching anything else that might happen in the future. Now, this type of technology has been advanced to the point where we can very efficiently and in real time reason about even fairly complex requirements, temporal requirements. In many cases, we can do this with low overhead and with limited resources, and this has successfully enabled a lot of recovery from software errors, such as enabling restarts or exits from infinite loops. But there is something that we need to watch very carefully when we try to do this type of thing on a spacecraft, and that is that it requires instrumentation here in order to send the state variables from the software to the monitor. And one of the reasons that we need to be careful about this is because some monitors report only property failure, yet we have noticed that in the case of spacecraft and in trying to reason about our own system health, it is equally important to report when properties pass, when you are satisfying, flying colors, all of your safety requirements. So we need to be careful to send enough information that we can determine both of those to a runtime observer. We also need to look at how we instrument the software or hardware, as the case may be, because we're talking about real-time systems, and we want to make sure that we don't do things like, for example, alter the timing behavior of these systems, right? We also need to make sure that we don't have a trade-off that we can't handle, such as being responsive and self-aware of certain things at the cost of utilizing advanced resources that we can't fly. So, for example, we are limited in terms of how powerful of a computer, how large of a database, how much overhead we can have. We need to be cognizant of these things. We also have to be aware, this was mentioned actually in one of the talks this morning, of the fact that a lot of these are designed in maybe an unintuitive specification language or something that is overly specialized to the system where it was originally designed to operate. So it's important that we think about the generality and the ability to adapt to different types of platforms and systems and updates of our current system. And finally, we have the problem that a lot of times these are set up to report only the outcomes of specifications. Now we need to be careful about that because it's very easy to get something like, hey guys, your lander just crashed. we're rather good at knowing that right now, right? It's the other stuff that happens before the lander crashes that we want to be better at knowing at, right? So these are the kinds of things we need to look at. In other words, we need these following requirements that I have on this slide. We need something that is realizable. It needs to have an easy expressive specification language that is generic and adaptable to our different platforms or updates to the current platforms. We heard in the keynote this morning the funny story about having to mail the entire chipset when someone makes one small update to a system. We need to avoid that kind of thing, right? It also needs to be responsive. We covered how these are real-time systems, so we need to be able to monitor in real time and detect deviations, and do this in a way that we can hopefully enable mitigation actions to be triggered. And finally, it needs to be unobtrusive. Now, this means something slightly different, of course, for each mission, but in general, it means that we need to still be able to pass whatever certification is required. We need to not make large changes that violate the constraints of functionality, timing, tolerances, cost, or other things like this, right? In other words, we need a responsive, realizable, unobtrusive unit. So we call that R2U2. And then the question arises, okay, we know what we need, so how do we do that? And in preliminary work, we've looked at how do we do that. In the case of unmanned aerial systems, such as the Swift all-electric UAS and the Dragon Eye, which you see pictured here with my colleagues Johan Schumann, who's here today, and NASA Ames UAS expert Corey Ippolito. But this is the spacecraft flight software workshop, right? So we want to know how do we do that for spacecraft, like small satellites, right? How do we adapt this to that mission? Well, on a high level, I'll go over the general architecture of R2U2. You can find more details in the papers cited at the bottom of the slides. We attempt to add the system health management framework capability through two major pieces of architecture. We pair temporal logic runtime monitors for very efficient temporal reasoning with Bayes nets for efficient decision making. So we accept specifications in metric temporal logic and also pastime MTL. We also allow users to write linear temporal logic, since that is an incredibly popular specification language. And we call it mission time LTL, because then when we encode the LTL, we take into account mission parameters to ensure that eventualities are fulfilled the way the specifier intended. And for each temporal formula specification, we encode it twice, once as an asynchronous or event-triggered runtime observer that returns either that it passed or that it failed as soon as we can possibly know. And we also encode it as a synchronous or time-triggered observer that returns true, false, or maybe, or you could also take maybe to mean I don't know yet. And it returns this at every tick of the system clock as a very useful liveness and sanity check. We pair the outcomes of these runtime observers with Bayes nets that are able to reason over these, filtered sensor data, other values, other Booleans we might get from the system, and then output the most likely health status and the probability of that status. So to give you a quick overview of what this looks like, which we implement in both hardware and software, here is an example pictorial representation of an R2U2 specification for a fluxgate magnetometer. So from the manual of the fluxgate magnetometer, we know that it can suffer these 5 errors. And so we create 6 temporal logic specifications that describe different sanity checks that would be tells of these errors occurring. And then we can feed their outputs through sensor nodes to a Bayes net that has health nodes for each of these possible errors. And so you can see here that the probability that there is a magnetometer sensor error is dependent upon the outcomes of these 2 temporal logic formulas and some other data as well in this case that's not in this picture. And this would help us determine with high probability whether or not we're suffering this error. We can do this in real time. And we create these specifications, as you can see, in a way that is hierarchical and structured, in a way that is compositional, and in a way that is cross-language. So we're combining temporal logic and probability here, right? This has been quite effective, actually, in our current work. For example, we are looking at deploying this, integrating it into NASA's Autonomy Operating System, which many of you might be interested to know is built on top of CFS-CFE, in a current project looking at better management for unmanned aerial systems. But we also want to be able to look at this in terms of spacecraft. And we also want to be able to take a minute to automate putting this on spacecraft. As Mike Aguilar highlighted earlier today, this is one of the things we need to focus on, is not having everything be a manual process, but when we learn certain lessons, automating that so that we can write specifications like the complex one you just saw for the fluxgate magnetometer for future missions and do less work. So going back to the Schiaparelli lander, we notice that, for example, rates are one of the things that we commonly want to have sanity checks for. You can't fall faster than gravity, right? So we want to have sanity checks for each type of place in the system where there might be a rate of change that should fall within some expected value, give or take sensor noise and that sort of thing. We've also noticed that we tend to write a lot of specifications to check ranges, right? So when you are in descend toward the planet mode, your altitude cannot be negative. Similarly, or I guess I should say oppositely, if you're in drill beneath the planet surface mode, your altitude is hopefully not positive, right? So for every subcomponent that we fly on these spacecraft, we have some range of values that we expect to get as output, and it's a fairly easy sanity check to make sure that we double check that each of the outputs we get are within these ranges before we use them for critical calculations going forward. We also have relationships that are pretty intuitive to be able to monitor. For example, if we deploy the parachute, then we know there is a very specific time later where we see expected changes in velocity reducing, right? If we fire the braking thrusters, again, we can predict over the next few units of time exactly what is going to happen to our velocity. So we can check that the relationship between these two things is as we expected. And we know if it's not, that either there's a problem with the spacecraft or there's a problem with us figuring out what's going on with the spacecraft, right? We also notice that we see a lot of control sequences, things that should happen given a certain command in a certain order. So for example, when the aircraft says, okay, I am now commanding a landing, then we should see something like we deploy the parachute, and then we eject the heat shield, and later we release the parachute, right? These things happen in a specific order. You never release the parachute before you deploy it, for example, and they're separated by other things we can usually check as well, by some period of time or some event, right? So that's another type of sanity check that we find that we often need and could potentially automate on board these systems. Finally, we look at consistency checks. And we heard a reminder of the keynote yesterday of how important it is to, for example, separate your main control software from your enabling autonomy software. But then it's also very important to have a consistency check running that these two things always agree on the state of your overall system, right? So if you, for example, have different mission modes, every subcomponent of your spacecraft that has a conception of what mode you're in should think you're in the same mode, right? If you're visiting waypoints, every system that has a notion of what waypoint you're at should think it's the same waypoint, right? If not, you have a problem. This is the kind of thing that we want to automate checking. So we need to expand the actually growing body of specification pattern research to patterns of runtime and for system health management. October also was the beginning of a new project, which we call Multiplatform, Multi-Architecture Runtime Verification of Autonomous Space Systems. This is the NASA Early Career Faculty Award, where we're looking at the question of what it would take to adopt R2U2 from our previous trials with UAS to expand it to work on things like small satellites, rovers, UAS and other planets, and this sort of thing. So I'll enumerate a few of the many questions that we hope to look at during the course of this 3-year effort. The first one is noticing that, especially when we are building small and cheap spacecraft, such as a CubeSat, a lot of times we'll use COTS components or otherwise things that are not rad hard. So this creates a challenge for making sure that we don't, for example, do harm because the runtime monitoring framework itself has experienced an error, right? We don't want to introduce our own bad data. So this is one reason why we look at running software and hardware implementations of R2U2 in parallel. But then it also raises the question of how to check the checkers, right? If these two things don't agree, how do we determine that? How do we determine which one's right and which one's wrong? Do we need to get into a situation where we need to devise a way of monitoring the health of the health monitors, right? And what does that look like? We also can make the observation that in space, differently from on Earth, where it's totally normal for someone to just send up like one UAS to do a single craft mission, in space that pretty much never happens, right? You always have a rover that is in view of a satellite. You would deploy CubeSats as a group or a swarm. You would have UAS working in tandem, right? There would be some way to have some kind of external observation of your system state. And as long as we have this external observation, then we should ask the question of, can we use that also for our own benefit? So is there a way of sanity checking what we believe to be true on board using observations that others can make of our craft, our own ship, right? And then, of course, we have to take into account the errors on board the other entities in the swarm or transmission errors or things like this, right? So that's not quite as simple of a question as it might at first seem. We also have to face differences in resource constraints. So this has also been covered in many talks, that there are differences between on Earth and things that we might launch in terms of power or the amount of CPU cycles available to us, memory, these sorts of things. Certainly telemetry bandwidth. We have to look at what kinds of things do we need to make sure to have the capacity to be able to analyze on board. And there was this very nice slide by Dan Gaines the other day where he pictured the Mars sols and how they line up with the work hours here at JPL and how responsive humans can be to that data, right? So we have this limited amount of human validation, and we need to integrate system health management with knowledge of those constraints so that we can be smart about how we use that. So I'll leave you with a series of open questions that we are looking to evaluate in the future on this project. So first, we're looking at what are specifications for runtime system health management. What does system health management mean, particularly as a first pass for small satellites, for small autonomous spacecraft? And how do we do things like reason about the differently harsh environmental conditions or radiation of space? How do we look at specification patterns and automating or semi-automating the extraction of specifications for different configurations of a system or for different mission parameters? How do we integrate swarm observations, external observations, in order to be able to be smarter about our own system health? And then how do we utilize the asset of parallel implementations of the same system health management framework in hardware and software to try to be more robust and also handle checking our own monitors to make sure that we aren't the source of bad data that may take down some future mission? So I welcome collaborations on this work and also questions.
Just a quick question. You said that you had to check whether it was falling faster than gravity.
Yeah.
Isn't it possible it could descend faster than gravity due to aerodynamic forces temporarily? Like, couldn't the wind push it down faster than gravity at some point?
Well, my point is that you can calculate an envelope, right, beforehand and say, you know, for any rate of change, for example, if it's outside this envelope, something is really wrong, right? So, you know, there's, obviously it's not going to be one floating point number that you test for equality. We all know how that works out, right? But there's going to be some reasonableness range, and you can calculate that before you launch any mission, right? And a lot of these sorts of sanity checks we need, what went wrong wasn't that something was like really close, right? It was that something was way off, right? So as long as we're better at catching those, we're still going to do better at mitigating some of these errors in the future.
Okay, thanks.
For the practicality of these systems, could you comment on what kind of size of a BaseNet you really need to have the system start being effective for monitoring a spacecraft level health?
So I think maybe Johan should chime in on this somewhat, because I have to say he is the person who designed, for example, the BaseNet that I showed on this slide.
Okay, so pretty much the size of the BaseNet depends on the number of signals you monitor, or the number of temporal observers you monitor, and the number of failure modes. So it could be up to a couple hundred for a complex system, but they exist, and we have kind of implemented both in hardware and software efficient ways of dealing with this reasoning process.
That seems computationally achievable?
Yes.
Yeah, I just wanted to comment. Sometimes as software developers, we don't get into the hazardous what would go wrong if, you know, especially with the hardware and software interfaces. And sometimes it seems kind of funny that, you know, a micro switch in a leg goes wrong and we lose a mission, or some little bobble in the instruments. Have you guys ever heard of something called HazOp? H-A-Z-O-P. It's called hazard operations. It's ancient. It's used on chemical plants and hydroelectric plants and whatever. And what it is it's a technique. It's just a word game. And I found it real effective with working with people that come out of school and hasn't done any kind of hazardous, you know, involvement with the spacecraft. In essence, what you do is, let's say you have a timer interrupt. And then you attach that timer interrupt. What if it goes too fast? What if it goes too slow? What if it goes to a DC ground? What if it goes to a DC high? You know, or what if it's random? And those are attributes you assign to something that's very particular. And then you play a mind game with what would happen to the system if these things occurred. And it's not, you know, FME, it's not FAMICA or anything that's really difficult to do. It's actually very simple to do around a tabletop, but it can really uncover some things that are really surprising. And that was HAZOP.
Thank you.
Thank you. Yes, that's it. Thank you, Kristin.
Thank you very much.